Hello and welcome to Lecture 4 of Oscillations in Phys 1201, and we're going to finish off by looking at some examples of simple harmonic oscillations other than a horizontal mass on a spring. To be able to assess whether something is going to execute simple harmonic oscillator, we need to be able to look at whether it's similar to a mass on a spring. And as we've seen, one of the defining features is the linear restoring force, right? So this Newton's second law that says ma is negative kx, right? That's just Newton's second law says ma is the sum of all the forces, and in this case that's just the spring force. And the negative is saying it's restoring, and it's x to the power of 1, so that's linear. And I'll just rearrange it slightly because it's going to turn out to be more convenient in this form to see what we need to see. Now, what we've seen in the last couple of lectures is that whenever this is the form of Newton's second law, it leads to a sinusoidal solution like this. And what's more, this 2 pi over t, which is like a frequency, is just the square root of k over m. So we've seen that, and I want to point out that this k over m here is appearing in both of these places. Now, what that tells us is that if the acceleration is negative any constant times the position, so, any constant like flurbity, if a is negative flurbity times x, then we will again get a cosine, or any sinusoidal function, as our answer, and the 2 pi over t is going to be the square root of flurbity. So we can recognize any time we have a linear restoring force, we know we'll get a sinusoidal position versus time, and out of Newton's second law, we can just read what 2 pi over the period is going to be. Armed with the knowledge we have now, it's finally time to look at the vertical mass on a spring, which in practice is the thing that's easier to set up than the horizontal mass on a spring. So we know that with no mass hanging on it, the spring has some equilibrium length, and I'm going to call that L naught, L sub 0. Okay, so that's the equilibrium length of the spring, the length it's at when there's no force applied on it. And when you hang a mass on it and slowly lower it until you find the place where the mass hangs stationary, then the spring is going to be at some new length that I'll call L sub e. It will have stretched by some amount that I'll call delta L sub e. Okay, and these sub e's are just to say that this is the place where the mass is at equilibrium, right? Where the sum of the forces on it is 0. So note, this is the location of the equilibrium position now for the oscillator, which is a different thing from the equilibrium length of the spring. It's easy to mix these up, but the spring has its own equilibrium length, which is the length it takes on when there's no force on it. But the place where the mass hangs stationary is the equilibrium position for this mass spring system. And just as it was convenient before to put our axes at the equilibrium position, it's going to be convenient to put our origin at the equilibrium position again. And so I'll just point out that at this position, and this position only, your sum of all the forces is just the spring force, which in my sign convention here is up, is positive because I've set up as positive, minus the weight of this mass here, and that those have to add up to 0 just at this position. So, to recap, here's our spring at its equilibrium length. Here's our mass hanging at its equilibrium position, so that the spring is stretched by delta LE, and when the mass is at this particular place, there's the free body diagram, just the spring force and the weight, and F net is 0. Or in other words, the spring force up and the weight down add up to 0. And I've set my axes at that location. Now let's think about the mass at any other position. So here I've displaced it up a little bit. See, there are the axes still. Delta L is smaller, and so the spring force would be weaker. The free body diagram would be exactly the same, except now because the spring force is smaller, F net points down. And so that means our sum of forces in the y is, it's still K delta L, not delta LE now. It's not that particular special delta L. It's just any old delta L minus mg equals, and it doesn't equal 0, it equals ma. All right, so this doesn't look like the simple harmonic oscillator equation, ma is negative kx, right? It doesn't look quite like it. And so at the moment, it doesn't look like this is going to necessarily turn out to be simple harmonic motion. But now there's a trick, because right here, this distance that the mass is displaced up, that's y. Right? That's what we would call y, the y position of the end of the spring. And notice that delta LE is just delta L plus y, right? Delta LE is just delta L plus y. You can see that right here. And so, or in other words, delta L is delta LE minus y. Well, so what? So that means we can rewrite this. We can say now we have K times delta LE minus y. I've just substituted this in for delta L minus mg, and all that equals ma. And let me just expand that out. ma is K delta LE minus ky minus mg. But wait a second, look, we've got K delta LE minus mg, and we know that K delta LE minus mg is 0. And so what we've got now is ma equals negative ky. A is negative k over my. Aha! Simple harmonic oscillator. And what's more, remember that when A is negative flurbity times x or y, whatever the coordinate is, then that means that our 2 pi over the period is the square root of flurbity. So not only do we know that this is going to be simple harmonic motion, but we know that we can solve for the period because it's going to be just the square root of k over m. But note that that's exactly the same it was for a horizontal mass on a spring. So what we see then is that taking your mass and spring and putting it vertically doesn't change anything. It doesn't change the frequency, and you still get simple harmonic oscillations. All it changes is the location of the equilibrium position. So I've mentioned the pendulum a few times, and part of the reason we're interested in them is, besides pendulums like what you would think of as a pendulum in an old-fashioned clock or something like that, systems that behave like pendulums are very common. Things like swings, or say wrecking balls. And let me just mention how annoyed I am that these days it's very difficult to find a picture of a wrecking ball without a person sitting on it. Anyway, there's no spring here. And so it's not at all obvious that this is going to behave like a mass on the end of a spring. Not obvious at all. And I'll warn you before I go through this that there are a few steps in this argument that are subtle, and that in the end we need to make an approximation. So this is a little tricky. I'm not going to pretend that this is simple. Anyway, here we've got our pendulum. We've got some object down on the end of a string or rope. We'll say the length of this is L, and at the moment it's sitting out at some angle theta from the vertical. And so the free body diagram looks like this. All we've got is the weight and the tension directed at some angle theta. And F net is actually a little subtle, because remember, this is on a circle. So there's going to be a component of the acceleration inwards, but it's also changing its speed, and so F net is at some funny angle. Now, it turns out this isn't going to cause us any difficulty, because we don't care about what's going on radially. We only care about what's going on tangentially, and so we can ignore everything radial. So let's look more closely at the free body diagram and use this fact that we don't care about the radial part of what's happening here. All we're worried about is the tangential part. So the tension is entirely radial. The weight you can break up into a radial and a tangential component, and now there's going to be the angle theta here. So from that triangle you can see, and I'm going to now work with a convention that everything counterclockwise is positive, that that component of the weight, which is our only tangential force, is mg sine theta, where this negative is because it points back clockwise, and I'm setting counterclockwise as positive. So here's my Newton's second law for the tangential component. It's just ma is negative mg sine theta. And we could write down the radial components, but who cares? It's not going to be important to us, so I'm not going to bother. Okay, so there's our Newton's second law. ma is mg sine theta, and these m's are going to go away in a moment. Here's where things get subtle. Think about this. We would like to relate our acceleration to how far the pendulum has moved over this way. So it's really this arc length here that I'm going to call s that we want to relate it to. And, you know, this is a funny shape, right? It's not a triangle because it's got a curve down here, but it's very similar to a triangle like this with the same angle theta. This side, which is our hypotenuse, we're making a right angle triangle, is L. So, I mean, this is not what this shape is, but as long as theta is small, we can approximate it that way. And so we can approximately get s. It's very similar to the length of this line here. And so that's why I made a right angle triangle, because we can now say that sine theta is about the opposite over the hypotenuse. So s over L is about sine theta. And that's only going to be true and only approximately true when theta is small. So here's the subtle approximation. And now that's handy because we can now replace the sine theta in here with s over L. And so there we go, and the masses go away, and I'm just going to rearrange this a little bit so that it looks like this. And note, this is like a equals negative g over L x, right? Because s is our displacement. And so we can see, hey, look, there's fluidity. So fluidity is g over L, and this has the right form for simple harmonic motion, negative fluidity times our displacement. And so we've shown approximately when theta is small that the pendulum will do simple harmonic oscillations, and we can solve for the period by saying that 2 pi over t is root of fluidity, which is g over L.